Chapter 30, Section 2, Interactive Reader, pages 473 through 480, 20 points. Stars, galaxies, and the universe. Stellar evolution. Key ideas. As you read this section, keep these questions in mind. How does a protostar become a star? How does a main sequence star generate energy? How does a star evolve after its main sequence stage? Page 473. What is luminosity? On the diagram, circle the main sequence. How do scientists study and classify stars? Highlight. A typical star exists for billions of years. For this reason, highlight, astronomers cannot observe one star for its entire lifetime. Instead, astronomers, highlight, study stars in different stages of development. Astronomers use this information to learn how stars change over time. Classifying stars. To classify stars, scientists measure temperature and luminosity. Highlight, luminosity is the total amount of energy that stars give off each second. Scientists have found a relationship between temperature and luminosity. Highlight, the graph that shows this relationship is the Hertzsprung-Russell diagram, or HR diagram. Continue highlighting. Astronomers plot the highest temperatures on the left. Continue highlighting. They plot the highest luminosities at the top. The temperature and luminosity of most stars fall in a diagonal band on the graph. Highlight. This band is called the main sequence. Continue highlighting. Stars in this band are called main sequence stars or dwarfs. Continue highlighting. The Sun is a main sequence star. Under the diagram, highlight, cool, dim, red stars are in the lower right. Hot, bright blue stars are in the upper left. Question number 1, what is luminosity? Answer, the total amount of energy a star gives off each second. A star gives off each second. Question 2, on the diagram, circle the main sequence. Use your highlighter to highlight the line that runs through the center of the picture, including where it says Sun and red dwarfs, all the way up to the top left. Highlight that line in the center of the picture. Page 474. What is one event that can cause a nebula to start to collapse? Jupiter's mass is very large. What is the most likely reason that we do not generally feel the effects of Jupiter's gravity on Earth? What is plasma? How do stars form? Highlight. A star begins in a nebula. Continue highlighting. A nebula is a cloud of gas and dust. Most nebulas contain 70% hydrogen, 28% helium, and 2% heavier elements. Highlight, an outside force such as the explosion of a nearby star may cause the nebula to start to collapse. Continue highlighting. The nebula may also start to collapse without a known force. Question 3, what is one event that can cause a nebula to start to collapse? Answer, the explosion of a nearby star. Again, the explosion of a nearby star. Highlight, nebulas follow Newton's law of universal gravitation. Continue highlighting. This law states that all objects in the universe attract each other. Continue highlighting. This force of attraction increases as the mass of an object increases. Continue highlighting. The force also increases when objects get closer together. Continue highlighting. Therefore, the attraction between the particles in a nebula increase as gravity pulls them closer together. The increased force of attraction pulls in more nearby particles. The mass continues to increase as more particles come together. Dense regions of matter build up in the nebula. Question 4. Jupiter's mass is very large. What is the most likely reason that we do not generally feel the effects of Jupiter's gravity on Earth? Answer. It is too far away. It is too far away. Over time, protostars. Over time, nebulas may form protostars. This process has many stages as described below. Gravity causes dense regions in the nebula to contract. As a result, any spin in the region increases. The shrinking, spinning region flattens into a disk called a protostar. Matter collects in the center of the protostar. As more matter enters the protostar, gravitational energy changes to heat. This heat energy increases the temperature of the protostar. The protostar continues to contract and increase in temperature for millions of years. Over time, the gas in the protostar becomes extremely hot. As a result, electrons in the gas separate from their parent atoms. Highlight. The nuclei and free electrons move independently. Continue highlighting. The gas becomes a plasma. Continue highlighting. Plasma is a hot gas that is made up of electrically charged particles. Continue highlighting. It has an equal number of positive ions and electrons. Question 5. What is plasma? Answer. A hot gas made of electrically charged particles. Again, a hot gas made of electrically charged particles. Page 475. What process begins when a star is born? What would happen to the star if it could not produce enough energy to balance the force of gravity? How does a main sequence star produce energy? The birth of a star. Highlight. Temperature continues to increase in a protostar to about 10 million degrees Celsius. Continue highlighting. At this temperature, nuclear fusion begins. High temperatures and pressures cause small atomic nuclei to combine into larger nuclei. Nuclear fusion releases large amounts of energy. Highlight. The start of fusion marks the birth of a star. Continue highlighting. Nuclear fusion can continue for billions of years. Question 6. What process begins when a star is born? Answer. Nuclear fusion. Again, answer. Nuclear fusion. A balancing act. Highlight. Fusion happens faster as gravity increases the pressure on the matter in the star. Continue highlighting. At the same time, the energy from fusion heats the gas in the star. Continue highlighting. The energy and hot gas push outward and resist the inward pull of gravity. Continue highlighting. These forces balance each other as shown below. Continue highlighting. This balance makes the star stable in size. Under the diagram, highlight. A main sequence star keeps a stable size for as long as it has enough hydrogen for fusion. Inside the diagram, outward force due to fusion and radiation. Outside the diagram, the force of gravity. Question 7, what would happen to the star if it could not produce enough energy to balance the force of gravity? Answer, it would shrink. It would shrink. What is the main sequence stage? Highlight. The longest stage in the life of a star is the main sequence stage. Continue highlighting. During this stage, nuclear fusion continues in the core of the star. Continue highlighting. Hydrogen fuses into helium and produces energy. Continue highlighting. A star with the same mass as the Sun stays on the main sequence for about 10 billion years. Stars with more mass fuse hydrogen more quickly. They may stay on the main sequence for only 10 million years. However, less massive stars can stay on the main sequence for hundreds of billions of years. Question 8, how does a main sequence star produce energy? Answer, fuses hydrogen into helium. Fuses hydrogen into helium. Page 476. In about how many years will the Sun leave the main sequence? What causes the outer shell of a star to expand after it leaves the main sequence? Why are giants very bright? The Sun and the main sequence. Our Sun has fused about 5% of its hydrogen over a period of 5 billion years. Highlight. After another 5 billion years, the rate of fusion in the core will decrease. Continue highlighting. The Sun's temperature and luminosity will change. Continue highlighting. At that time, the Sun will leave the main sequence. Question 9. In about how many years will the Sun leave the main sequence? Answer, 5 billion years. 5 billion years. How do stars leave the main sequence? Eventually, stars leave the main sequence. This process starts when about 20% of the hydrogen atoms in a star's core have fused into helium atoms. This process has several stages. 1. Gravity causes the core of the star to contract. 2. The contraction heats the core. The helium core transfers energy to a shell of hydrogen around the core. 3. The energy causes hydrogen fusion to continue in the outer layers of the star. 4. The hydrogen fusion radiates large amounts of energy outward. 5. Highlight. The radiation causes the outer shell of the star to expand. Question 10. What causes the outer shell of a star to expand after it leaves main sequence? Answer. Radiation from hydrogen fusion. Radiation from hydrogen fusion causes the outer shell to expand. Causes the outer shell to expand. Again, radiation from hydrogen fusion causes the outer shell to expand. Giant stars. Highlight. A star's shell of gases cools as it expands. Continue highlighting. As the gases get cooler, their glow becomes reddish. Continue highlighting. The star becomes larger and redder. Continue highlighting. These large red stars are called giants. They are bigger than main sequence stars of the same surface temperature. Highlight. Giant stars have large surface areas. Continue highlighting. For this reason, they are very bright. Giants can be more than 10 times larger than the sun. Highlight. Over time, stars with the same mass as the sun will become giants. Continue highlighting. As these stars become larger and cooler, they move off the main sequence. Question 11. Why are giants very bright? Answer. They have large surface areas. They have large surface areas. Supergiants. Highlight. Massive stars become larger than giants as they leave the main sequence. Continue highlighting. These very luminous stars are called supergiants. Supergiants can be more than 100 times larger than the sun. The supergiant Betelgeuse is 1,000 times larger than the sun. Supergiants are easy to find in the night sky because they are so bright. However, their surfaces are cool compared to the surface of other stars. Page 477. When does fusion in the core of a sun-like star stop? What is a white dwarf? What are the final stages of a sun-like star? Highlight. The final stages in a star's life cycle depend on the size of the star. Highlight. Stars about the size of the sun follow a similar cycle. Continue highlighting. Fusion in the core stops when helium atoms have fused into carbon and oxygen. Continue highlighting. The supply of energy from fusion drops and the star enters its final stages. Final stages of sun-like stars. Highlight. Red giant. Highlight. Planetary nebula. Highlight. White dwarf. Highlight. Possible nova or supernova. Question 12. When does fusion in the core of a sun-like star stop? Answer. When helium has fused into carbon and oxygen. Again, when helium has fused into carbon and oxygen. Planetary nebulas. Highlight. In its final stages, a star's outer gases drift away. Continue highlighting. The remaining core heats these gases. Continue highlighting. The gases appear as a planetary nebula. A planetary nebula is a cloud of gas that forms around a dying star. These clouds may form different shapes around the star, such as a sphere or a ring. White dwarfs. Highlight. Over time, the gases in the planetary nebula drift away. Continue highlighting. Gravity pulls the remaining matter in the star inward. Continue highlighting. The matter moves inward until it cannot contract anymore. Continue highlighting. A hot, dense core of matter called a white dwarf remains. White dwarfs shine for billions of years before they cool completely. Highlight. White dwarfs are hot but dim. As white dwarfs cool, they lose brightness. This is the final stage in the life cycle of many stars. Question 13. What is a white dwarf? The remaining matter from a dying star that has been pulled into a hot, dense core. That has been pulled into a hot, dense core. Again, the remaining matter from a dying star that has been pulled into a hot, dense core. Novas. Some white dwarf stars are part of a binary star system. Highlight: a binary star system involves two stars. For example, a white dwarf may revolve around a red giant. The gravity of the white dwarf may pull gases from the red giant. These gases collect on the surface of the white dwarf and build up pressure. Highlight: this pressure may cause large explosions which release energy and matter into space. Continue highlighting: this release of energy is called a nova. Continue highlighting: a nova may cause a star to become much brighter than it normally is. Continue highlighting: however, the nova starts to fade after a few days. Continue highlighting: novas do not usually destroy the binary star system. Thus, a white dwarf may become a nova many times. Page 478. Name one difference between a nova and a supernova. What is the last element that forms by nuclear fusion in massive stars? Supernovas. A white dwarf in a binary system may also become a supernova. Highlight: a supernova is a star that explodes and blows itself apart. The steps below describe how a supernova forms. 1. A white dwarf collects mass on its surface from a nearby red giant. 2. The gravity pulling on the mass overpowers the outward pressure. 3. The star collapses. It becomes so dense that the outer layers explode outward. Highlight: supernovas are much more violent than novas. Continue highlighting: the explosion of a supernova destroys the white dwarf star. Continue highlighting: it may also destroy much of the red giant. Question 14. Name one difference between a nova and a supernova. Novas usually do not destroy the star. Novas usually do not destroy the star. Supernovas destroy the star. Supernovas destroy the star. What are the final stages of massive stars? Some stars have masses more than 8 times the mass of the Sun. The final stages of these massive stars are different from the final stages of less massive stars. Highlight: red supergiant. Highlight: supernova. Highlight: neutron star or black hole. Supernovas and massive stars. Only a small percentage of white dwarfs become supernovas. However, highlight: massive stars become supernovas as part of their life cycle. Continue highlighting: after the supergiant stage, these stars contract very quickly. Continue highlighting: the collapse of a massive star creates very high pressure and temperatures. Continue highlighting: nuclear fusion begins again. Continue highlighting: this time carbon atoms fuse into heavier elements such as oxygen, magnesium, or silicon. Continue highlighting: fusion continues until the core is made of iron. Continue highlighting: iron has a very stable nuclear structure. Therefore, the fusion of iron takes energy from the star instead of releasing energy. Highlight: this star loses its supply of fuel and the core begins to collapse. The collapse releases energy. This energy moves to the outer layers of the star. Highlight: the outer layers explode outward with great force in a supernova. Question 15. What is the last element that forms by nuclear fusion in massive stars? Answer: iron. Page 479. Question: did the object in the picture form from a sun-like star or a massive star? How do you know? Neutron stars. Highlight: massive stars do not become white dwarfs. Continue highlighting: after a supernova, the core may become small, dense ball of neutrons called a neutron star. Continue highlighting. Neutron stars spin very quickly. Pulsars. Some neutron stars emit a beam of radio waves. These neutron stars are called pulsars. A pulsar rotates or spins. As it spins, its beam sweeps across space. Scientists can detect the beam every time it sweeps past Earth. The star rotates between each pulse they detect. Newly formed pulsars often have the remains of a supernova around them, as shown below. However, most known pulsars are very old. The supernova remains have gone away. Only the spinning star is left. Highlight next to the picture. The remains of a supernova explosion still surround this pulsar. Question 16. Did the object in the picture form from a sun-like star or a massive star? How do you know? Massive star, because sun-like stars do not go supernova. Again, massive star, because sun-like stars do not go supernova. Black holes. After a supernova, some massive stars leave a core that is more than 3 times the sun's mass. In this case, the star may contract more because of gravity. Highlight. This force crushes the dense core and leaves a black hole. Continue highlighting. The gravitational pull of a black hole is very strong. Continue highlighting. Not even light can escape. Black holes are hard to find because they do not emit light. Highlight. However, black holes have effects on nearby stars. Continue highlighting. The black hole pulls matter from the star. Continue highlighting. The matter swirls around the black hole before being absorbed. Continue highlighting. The matter becomes very hot and releases X-rays. Astronomers can detect these X-rays. Then astronomers try to find the object affecting the star. The star's motion may show that a massive invisible object is nearby. Astronomers conclude that the object is a black hole. Page 480. How can scientists detect a black hole if it does not emit light? Complete the Venn diagram below to compare sun-like stars and massive stars. What is the main force that causes a protostar to become a star? Over time, how does the amount of hydrogen in a star change? Explain your answer. Question number 1. Answer can be found on page 479. Material from stars that is pulled into a black hole. Material from stars that is pulled into a black hole swirl around and are heated, giving X-rays. Swirl around and are heated, giving X-rays. Again, material from stars that are pulled into black holes swirl around and are heated, giving X-rays. Question 2. Answers can be found pages 476 through 478. Under a sun-like star, medium mass, longer life, white dwarf. Again, medium mass, longer life, white dwarf. In the center, nuclear fusion, main sequence, giant or supergiant. Nuclear fusion, main sequence, giant or supergiant. Under massive stars, high mass, short life, supernova. high mass, short life, supernova. Question 3. Answer can be found on page 475. Gravity that causes nuclear fusion. Gravity that causes nuclear fusion. Question 4. Answer can be found on pages 475 to 476. Hydrogen decreases because it is being converted. Hydrogen decreases because it is being converted to helium and energy. To helium and energy. Again, hydrogen decreases because it is being converted to helium and energy.